We're on. Do you hear me?
Yeah. Yep.
Okay. How much did you read?
I was able to cover up. I have the integration.
Mhm.
That was covered. I did not quite get through the convex neighborhoods, but I touched upon the geodesics, and I.
So you just read. You read what's in the book, right?
Yeah.
Okay.
And I sort of looked at your notes as well.
Mm-hmm. That's okay.
And then I also, I had a little bit less time this week.
Yeah.
So I went out to the field a bunch. But I also did like parallel transport. I spent some time. Last week there weren't any good videos, but this week the Frederick Schooler's videos were.
Schuller.
He has on connections and on
yeah, right.
parallel transport.
Yeah.
So very derivative.
He doesn't prove a lot of things, but he explains well.
It doesn't what?
He doesn't prove a lot of things, but he explains well.
Yes. Yeah.
What about you?
I read things except convex neighborhood, a marginal understanding of knowing fields.
Okay. Yeah.
But
in
what counts
okay.
as
Yeah.
what
So.
reading?
Difficult to say. I mean, even if I give you any problems on Riemannian geometry, the range of difficulty is extremely high. So it's difficult to say. Depends on what you're going to do in the future. Like if you're interested in general relativity, for example, then you have to be somewhat of a master in Riemannian geometry, right? But if you're going to do like typical high energy stuff or something like that, then not so much. But still, it's useful.
You were saying if you're interested in general relativity, you need to be a master of differential geometry, and if you're what, then
of Riemannian geometry specifically. But
yeah. And if you're, and what was the?
But if it's like high energy stuff,
what did you follow?
Like the usual.
What did you follow that with?
I said that it's if you're interested in like high energy stuff, usual quantum field theory and particles, then not so much geometry. But it's getting a lot more popular lately, right? With all the topological materials and gravitational anomalies and whatever. So it is slowly seeping into all the areas of physics. All right. And in mechanics, in this book later on, we're not really going to use Riemannian geometry, so it's not super important for this material, but it is useful in general, which is why I included more material in my notes than the book.
It's useful for other things. It's also used in like all sorts of machine learning stuff.
I have not heard about that, but okay. Everything is used everywhere these days.
Yeah.
Okay, so there's one thing that I wanted to mention, which is important, which I forgot. Towards the end here. What's this? I described tensors as sections of the tensor bundle, right? So they are basically a bunch of covector fields times a bunch of vector fields. Okay. And there is another description of this which is very important, which is that this was the notation for tensors of type Rs and manifold, and the statement was that tensors are C-infinity linear homomorphisms, right? Maps from a bunch of vector fields and covector fields to functions. Right. So it's C-infinity from vector fields to C-infinity. Okay. Did you read about this?
Yeah.
Does this make sense?
Mm-hmm.
Laurent,
Yeah.
do you understand what this means and why this is?
That you can take an infinite amount of derivatives and you still have.
No, so this is more complicated. So this means that this is a C-infinity, well, this and that too are C-infinity modules, right? C-infinity is a ring. It's a structure where you can add and multiply things, right? You cannot divide by a function in general because it can have zeros. And the ring module is basically a structure on which a ring can act, right? So I can take an object like this and I can multiply it by an element of the ring. So for example, vector fields are, like real vector fields are R modules, right? Because I can take a vector and multiply it by a number. And in the same way, tensors are going to be C-infinity modules because I can take a tensor and multiply it by a function, i.e. multiply it by a number at every point of the manifold, right? So it's a pretty natural generalization of a vector space manifolds. And now this subscript here is super important because without this, you know, I could take, I don't know, I could take a vector field, I could take some metric and square it, integrate it over the volume, and get a number. A number is also a function, right? So that would be a homomorphism of this type. But the statement that it's C-infinity linear and not just linear over numbers means that this tensor, if I take a function and multiply, you know, whatever the arguments were, x1, and I act on this with the same tensor, this action commutes with the multiplication by the function. So this is f times t. Okay. So, as an example, I can take Rn. Let's take Rn. I can take a vector field, and I can apply like d by dx, right, to this vector field. And that also gives me a vector field, of course, just as you would do in physics. Right? But is this a tensor? Right? How do you prove that it's not a tensor? Usually, differential operators are not thought to be tensors, right? So, how do you prove that it's not a tensor? Fiber-wise, it's a map from vectors to vectors. So you would assume, maybe, that it's a type 1-1 tensor, right? But it's not because it's not C-infinity linear, which means that if I take this vector field and I multiply it by a function, this is not going to be equal to f, not going to be equal to f times dxx, right? But it's really equal to dx f times x and then plus this. So being C infinity linear basically means that first it's a local object, it's a local operation, right? Because if I take this f to be like a small bump function around some point, then I can isolate all the information contained in a small neighborhood at that point, right? In this x. And the result will still be basically the same up to multiplication by a number. So that means that it doesn't care, it's a local object, right? Like it doesn't contain integrals or anything like that. And then the fact that that this bump function can be arbitrary, which means that it can not just multiply by a number, but it can change all the derivatives, higher derivatives, etc. It means that this object also, the tensor cannot depend on any derivatives of whatever it's acting on, right? So it's not a differential operator, it's not an integral operator. Basically, the only thing it can be is multiplication by something, which is what tensors were initially. So this is a useful alternative definition of tensors because, for example, the curvature tensor introduced at the end of the Riemannian geometry chapter, it's not proven there. I think they just say like one sentence how to prove that it's a tensor. But this is how you prove that it's a tensor. You act with it on a vector field multiplied by a function, and you just check that the result does not contain any derivatives of that function. All the derivatives cancel, right? Which is not obvious if the curvature is like nabla y x or something else. In general, this would be a second-order differential operator. Why is it a tensor is not clear. But more on that later. One more thing, which I wanted you to remember, was that if I have a volume form, what's the notation for a volume form in the book?
In Abraham and Marston?
Yeah. New or something? Oh, maybe it's omega. It's big omega, I think.
Yeah, that's what it is.
Yeah. So if I take the Lie derivative of that along a vector field, what do I get? What does this mean intuitively? Do you have a mental picture of this?
You get the divergence.
Yeah, but why? So what's the mental picture for this? What does divergence measure? For example, if this is 0, what does that mean?
It means that there's no vectors leaving the volume pointing out of the, like, I don't know how to.
So remember the formula for the Lie derivative in terms of pullbacks. Okay. This means, this is just an infinitesimal version of the statement that the pullback of omega along the flow of this vector field is again omega, right? So omega is invariant under the flow of this vector field. Okay. So the volume is conserved by this vector field. As you flow, as you move points along the flow of the vector field, if you take like a patch of this manifold and imagine the points as being the molecules of a fluid, which is flowing along the vector field x, i.e. x is the velocity of the fluid at every point. Then this patch can change its shape somehow, but the volume will stay constant, whatever this volume form is. but in general, this volume is not preserved, of course, and this. But of course, the Lie derivative of a top form is still a top form, and any top form is proportional to the volume form, right? So there exists a function which multiplied by the volume form is equal to this, and we just define the divergence that way. So in the flat case, you can just check explicitly that this is the usual divergence. Okay. In general, it's star d star. As a form. Oh, that's wrong. Oh, x is vector. Right. Yeah. Is that clear? Laurent?
Yeah,
Is that a good picture?
the one on the bottom.
Yeah.
Yeah, good enough. I understood it.
So, for example, in hydrodynamics of ideal fluids, ideal incompressible fluids, incompressibility means that locally the volume of the fluid cannot change, right? Which by this formula means that the divergence of the velocity field has to be zero. So in hydrodynamics books, you will see this condition being called incompressibility. Not clear why, but this is why. There's again, this is an infinitesimal, differential form of that statement. There's a finite form, which is what? If this is the differential form, then what's the integral form? Is all, yeah. Yeah, if I take a closed surface, right, like a sphere, inside that volume, then the flux of the vector field through any closed surface must be zero. So, kind of mass is not being created inside of this volume. But in general, if some mass is generated, then this is going to be r dot, right? And this is called the, or minus r dot. This is called the continuity equation. And then this is replaced by d by dt integral rho dv. So just mass. And in this form, this should be obvious, right? This is the flux of matter, how much is flowing out, and this is literally the rate of the decrease of the mass. Okay. Any questions about integration? I think that should be pretty easy. The only interesting thing there is the Stokes theorem, of course. Any questions? Have you seen all the classical Stokes theorems before? Because if you haven't, then this would have been a lot more difficult to read. Right?
And then the general Stokes.
Okay, in differential forms.
Yeah.
What is?
Say by a feeling depends on.
What's the question?
What's the little symbol that right after the equal sign before the integral on rho dv?
d by dt. Time.
Oh.
Derivative.
Oh. Okay.
Yeah. Okay. Do any of you know any complex analysis? No. Okay. Well, if you do, then you would have at least the Cauchy integral formula. Yes. well then, the main foundational theorem of complex analysis, it's not called the fundamental theorem of complex analysis, but it probably should be, is that if I have an analytic function and I integrate it over a closed pointer, and it's analytic everywhere inside of that pointer, right? Then the result is going to be 0. Right? This is a version of the Stokes theorem. Yeah. If you just write it out in real coordinates, x and y, then it will be the Green's theorem. But you can also consider differential forms of this type. When is this closed? When is this closed? Well, a basis of differential forms in the plane is given by dz and dz bar, which is dx plus I dy and dx minus I dy. And so d of f dz is obviously by the usual rules of external differentiation, which is df by dz bar, and then dz bar dz. Right. This is just proportional to the volume in the plane, the area form. And this d by dz bar is dx f minus I d bar. So that means that this form is closed if and only if f is holomorphic. D by dz bar of f equals 0. This being 0 are the Cauchy-Riemann conditions.
The form is closed if and only if what?
If the function is holomorphic, analytic. And if it is, then this is an integral over the boundary of some domain, inside of which everything is defined as analytic. And by Stokes' theorem, it is equal to the integral over the domain itself of d of that one, okay, which is 0. So, yeah. And the Cauchy integral formula with the residue can be derived the same way, but if you have a singularity, then you have to like make a little circle around it, integrate over the rest using the Stokes theorem, and then take the radius of the circle to 0 and look at what the limiting expression is, and you'll get the residue. Okay. Anyway, Riemannian geometry. So what's a metric? What's a metric? What's a metric? Okay. Right. Yeah.
Or if it's Riemannian,
so we have G, which is 0 to okay. So, for example, in Rn, we can define different dot products, right? The usual dot product is x and y is the sum of x, I, y, I. Right? But this is not the only dot product you can define. You can define any dot product like this with some matrix Bij, where this matrix has to be positive definite. Right? So that means that the eigenvalues of this matrix are positive. Of course, you have to be, with this formula, for example, you have to be careful using it, because if I go to a different basis, not the standard basis in Rn, but to a different basis, then this expression will no longer work. Okay. Like, obviously, if I go to polar coordinates, for example, and I want to multiply vectors, I have a vector x with components xr and x theta, and then yr and y theta. If I want to compute the dot product of these two in the plane, it's not like that. It's not just the pairwise products. Which means that the metric transforms a little bit more complicated than the usual matrix, because if this was a real identity matrix here, the identity matrix is the identity matrix on any basis, right? But it clearly doesn't work. So that's kind of a proof that the metric cannot be a 1-1 tensor. It has to be a 0-2 tensor. Or, yeah. And so on a manifold, it's just the same thing, but fiber-wise. And I want to make a general philosophical note, which is that in geometry, there are a few different ways of adding some structure to a manifold like this, and they are all similar in that they provide a natural isomorphism between Tm, the tangent bundle, and the cotangent bundle. Okay, so usually you got the tangent space, you got the cotangent space. The cotangent space is the space of linear functionals on the tangent space, and we know that they are isomorphic as vector spaces, right? But there is no natural isomorphism, by which I mean there's no obvious choice of an isomorphism based on the structure that you have just on a bare manifold. Okay? So if you want to somehow identify vectors and covectors canonically, you need some more additional structure, which gives you an isomorphism between those two things. Okay? And Riemannian geometry provides you with one, which is that you take a vector and you send it to G, I, J, X, right? And this is a covector. Let's call this I. Okay. By the way, is the index notation good for everybody? So the lower indices are covectors. So this and this are completely different objects, right? They live in different bundles, in different spaces. But the metric lets us lower and raise the indices like this, thus giving a nice morphism between those two things. And this is called the musical isomorphism. So the lowering of indices is the flat symbol, and then backwards xi is going to be gij, xj, where this g with upper indices is just the inverse matrix. So it's just fiber-wise, you take the matrix of numbers gij and you invert it, and you get the upper gij. And this is called sharp. Physicists always get annoyed with mathematicians using notation like that. And if you do like pure Riemannian geometry, general relativity, with no additional structure whatsoever, this index notation is fine. There's not many ways to get yourself confused. You don't really ever need to take derivatives of the flat mapping, in which case you would need a separate notation for the mapping itself to take derivatives of it. But when you have more structure, like some field bundles or the same manifold fermions or whatever, then you get a lot. You start getting a lot of different indices. You have one index for the Riemannian part, one index for the Lorentzian part, one index for something else, some topological parts, and then just gets confusing. So the index notation is not always so easy to get around. Also, among students, the index notation usually leads you to think of these as numbers, which they are not, right? They are only numbers when you pick a certain basis. But it's better to think of them as just abstract objects. This one has two indices. If I feed a certain basis of vector fields into this guy, I will get numbers, yes. But we can just think of this object as completely abstract. The two indices are not there to denote an array of numbers. They are there to denote the slots into which I can feed vectors, right? And that's it. That's how. Do you know Wald? Bob Wald?
Yeah.
Yeah. So he's a proponent of this notation. He's calling it the abstract index notation, which is a way to basically get around this classical thinking with numbers. So basically, in all of your proofs, even if you're using the index notation, if all the summations and everything that you do is correct, like it satisfies the Einstein summation rules, upper to lower, etc., then there's no way you will break the tensorial structure of all of your equations. There's no way to make a mistake, which means that even if your calculations were initially local, because you were seemingly using index notation, right? They are actually not, because it doesn't matter what basis you use, because you know that everything is tensorial, therefore automatically it doesn't depend on the basis, right? And the chart. Okay, that's that. Now, what else? Connections, right? Do you guys have a mental picture of connections? What they are needed for? Why can't we use partial derivatives? Huh?
If you apply to a vector,
They measure, they're like connected to curvature.
Yeah, but that's later on. But fundamental, why do we need covariant derivatives? Hmm?
If you do partial yeah, you think it has
I can't hear anything. I don't know what's being said.
It was not super insightful, but yeah. So the fundamental picture here is the following: we have a manifold, and we have the tangent spaces or the tensor bundles above it, fibers right above it. Okay. And let's say this is a curve, right, along which I want to differentiate. Okay. So we can have a tensor. Let's call this big T, which is which depends on some parameter T, and it belongs at every point in time to the fiber. What was the notation? T like that, and above the curve at time T. Okay. And I want to ask, does this make sense? Does this make sense? How do I define this object? And naively, you would do this. You would take T of T plus delta T minus T divided by delta T, and then limit, right? But what's the problem here?
There's no natural, so associate differences in different fibers.
Right. So they belong to different fibers, right? These objects are, you can think of them as objects of vector spaces, but they are two different vector spaces, right? Which means that you cannot subtract one from the other. But if we had some isomorphism, some canonical isomorphism, again, between those two vector spaces, right? Then we could have kind of pulled back this tensor to here and compared it to this one, and then taking the derivative. So the way to provide isomorphisms between all the different fibers of this bundle is called a connection. So it connects all the fibers between each other. Right? Of course, it has to do it in some consistent way, so that if you connect from fiber 1 to 2 and then from 2 to 3, it should be the same as from 1 to 3, etc. And having a metric turns out it gives you one canonical connection. So you have to impose some special conditions on the connection for it to be unique to that metric. That's called the fundamental theorem of Riemannian geometry, the proof that it's actually unique. And as you can see from, yeah.
You were cutting up part of it. You just said that the metric gives you the beginning of the parameters to create that isomorphism.
Yeah. So the metric, if you read the book, you saw that the metric defines one canonical connection on the manifold. So yeah. So in general, any connection can be compared to locally to a usual partial derivative, right? So we can take d by dxk, the vector field, right? Basis vector field local, and differentiate it along d by dxk covariantly, and we will get again a vector field which can locally be expanded in the same basis, right? So this is going to be a set of numbers, a set of coefficients here that depend on j, k, and then summed over some index, the d by dxi, right? And these guys are called the Christoffel symbol. In general, if I have two different connections, so say I have a nabla and a nabla tilde, and I act on some vector field, let's say y, and I'm acting on x, then the result is going to be a tensor. Okay. Why is the result a tensor? Because let's use the same definition of tensors that I talked about earlier. If I act on fx with this thing, then in the definition of the connection, I have that the connection along y, nabla along y, acting on the function is the same as the partial derivative, as the usual action of the vector field, right? So this is going to be nabla f and x minus nabla tilde f and x, and then plus f times nabla minus nabla tilde x, right? But these guys are the same because they are both equal to y f. Right? So this cancels, Huh? Yeah, they are different connections, but acting on functions, they are the same, right? Because functions are not sections of a vector bundle. Or, you know, you think of them as sections of some trivial vector bundle where there is a canonical identification of real numbers with real numbers. But this implies that F commutes with the action of the difference of any two connections on this manifold or bundle, and therefore the difference of any two connections is a tensor. Okay? And it's a tensor acting on vector fields, spitting out vector fields, but it also depends on y. You can also check that if I put f in here, multiply y by an f, I'll get the same result. I mean, that should be obvious from the definitions of the nublos, which means that it's an object which is a tensor in both x and y and spits out numbers, i.e. a tensor of type 1, 2. Right? So it takes in two vectors, spits out a vector, 1, 2. So this will be called C of x and y. Okay. This I k x k y. And of course, I have to define what the correct order is. Let's see. It's this. In Riemannian geometry, for the connection that we care about in Riemannian geometry, related to the connection, this turns out to be symmetric, so it doesn't matter how I write it. But in general, it is. In geometry books, you always see the warning that Christoffel symbols are not a tensor. They don't transform like a tensor. What's the problem, right? No, but they take so the Christoffel symbols. What they are doing is they take the nubla and they compare it to the partial derivative, which is locally connecting, right? No problem. And they just prove that the result is a tensor. Yeah. So why do people say that Christoffel symbols are not a tensor? Yeah, so the answer is because the partial derivative is locally connecting, but it's not globally connecting. That's still important. There's no way to just stitch partial derivatives in different charts. It's not even clear how to match the basic vector with the coordinates. Right? So the Christoffel symbols are not tensors because you're not comparing to a connection. You're comparing to some local object, partial derivatives. Right? Okay. But in some proofs, it is important. So, for example, this means that if I take any two connections and I define the Christoffel symbols this way, and I take the difference of the Christoffel symbols of those two connections, this is going to be a tensor, right? And that's important in some proofs. For example, when you take a manifold and you deform the metric, or you deform the connection somehow, then to do actual computations, to compute, for example, how does the curvature deform when I deform the metric in a certain way? You need to take variations of the Christoffel symbols, for example. And it helps a lot to know that the variations of the Christoffel symbols, as opposed to the Christoffels themselves, are actually tensors. Okay. Yeah. So what are the conditions that we need to impose on the connection to fix it? If we have a metric, how do I fix a canonical Levi-Civita connection defined by that metric? Oh, also the theorem that we read before about differential operators. What was the name of it all the time? Wilmore, right? Yeah. Which was saying that if I have a differential operator on tensors, which is defined consistently on functions of vector fields, then it can be uniquely continued to all tensors. Do you remember this? It was somewhere in. Oh, it was somewhere in vector field and Lie drifters. You don't remember?
This is the week I was out sick.
Oh, I see.
That's how I remember it.
Yeah, if we have a differential operator that acts on functions and vector fields, so it maps functions to functions and vector fields to vector fields, such that it's consistent, by which I mean that it satisfies the Leibniz rule on this level. The only Leibniz rule which is relevant here, well, first of all, you can take two functions and do the Leibniz rule, right? And then you can take the function multiplied by a vector field, and then you should have the same Leibniz rule, right? F dx and plus okay. Then the statement is that it can be uniquely continued to all tensors. Okay. Oh, there's one more condition, which is the derivative of delta of the delta tensor has to be 0. Okay. And the fact that the derivative of the delta tensor has to be 0 lets you extract from differentiation of the vector fields the differentiation of covector fields. Because if you multiply, if you act with a covector on a vector in the function, you know how to act in functions. Therefore, you can kind of invert that operation to extract how D acts on covectors. And after that, you can just take any tensor, locally expanded as a tensor product of vectors and covectors, and just act by the Leibniz rule. That's the whole thing. And that is unique just because there's an explicit formula for it, which is the Leibniz rule. So this gives us the connection acting on all tensors. Like if we know how to compute covariant derivatives of functions, which is just the usual Lie derivative, and vectors, which is the partial derivative plus Christophel's, then we also know how to act on any tensor, right? So for example, if I take nabla I of some tensor, of type 1, 1, let's say here. Okay. What is the answer? So on vectors, it would be like this. We di k, and then plus gamma I k j. On long forms, it's going to be with a minus sign. I of j minus gamma. We look at the lower indices, ij, and then the other one is on. Can you guess if I have two indices of this type? What's the one thing? Yeah, you just repeat, add a term, with the correct sign for each index. With a plus for contravariant index, minus for covariant index. Minus gamma I j and L T K L is for this index, and plus gamma I K L T L. Okay. Etc. So the conditions on the Levi-Civita connection are the following. It has to be compatible with the metric. What does that mean? So the compatibility with the metric is this: if I take any two vector fields and I take the dot product of those two vector fields, which means I take G, act on X and Y, right? And the result is a function. Okay? And I can take the nabla of that function, which is the same as the partial derivative. The requirement is that this has to satisfy the Leibniz rule, as if nabla can be to G and act on a product of X and Y, right? So G of nabla X, Y equals G of plus E of X nabla Y. Of course, this has to be nabla along some vector G. Right? If you write this out in components, then this just means that nabla G is 0. So the covariant derivative of the metric itself along any vector field is 0. And then it turns out that this is not enough. This does not fix a unique metric. Yeah. So the second requirement is torsionlessness condition, which is what?
The determinant of the metric has to be positive.
No, that's just positivity. Right?
Positive.
That's it being a metric.
Yeah.
Riemannian metric. It can be relaxed, like in general relativity. The metric you care about is Lorentzian.
Non-degenerate.
So it's not actually, it's not actually positive, but it's non-degenerate. That's called the pseudo-Riemannian manifold. But all the more complicated results about geodesics and convex neighborhoods and all of that stuff is much more complicated than pseudo-Riemannian manifolds, which is why mathematically Riemannian manifolds are a lot more fundamental, even though on the initial steps of constructing the metric and connection, it looks exactly the same. What? Right. Zero, right? Right. What does this mean in components? Well, in terms of partial derivatives, this will be just like xi and then di yj. But then this expression is going to be at the end. Yeah, it equals the commutator. Yeah. So basically, the commutator, if you just expand it in coordinates, it's exactly the partial terms of the nublus, and all the Christoffels must cancel. But in terms of the Christoffels, it's just, we just saw switching x and y is the same as switching the lower two indices. requiring that the Christoffels are symmetric in the local dimensions. And then from this, you just substitute coordinate fields or something like that, and you get an explicit expression for the gammas in terms of the metric, which in itself proves that it's unique, because you are able to obtain an explicit expression for it from these conditions, which means that it exists and is unique given by that formula, which is
Okay.
yeah.
Just off the it's plus K. But I mean, it's plus.
Yeah. It is useful to memorize this expression when you're doing the Riemannian geometry, but at this point that's super important. Just useful to know that there are these. This is called the fundamental theorem of Riemannian geometry. Not really a theorem because it's a one-line proof, but it conceptually is saying that if you have a Riemannian metric on a manifold, that gives you a natural connection. So maybe you should go on. Okay. About torsion, one note. Torsion actually comes up in some defect theory in physics, related to defects in crystals and stuff like that. It says if I take closed loop and I take the tangent space at the base of the loop, right? This is the loop in the manifold. And I take a vector in a tangent space, and I do parallel transport along the loop. Parallel transport is defined by the connection. Right? The connection provides us the isomorphisms between the different the neighboring tangent spaces. And when I get back, what do I get? Right, so this is like, let's call this tau, this transformation, the parallel transport along this loop, let's call this tau, and this tau acting on the vector is going to consist of two parts in general. It's going to consist of some mapping R of x, and then some mapping theta of x. And this R of x is if the size of this loop is like epsilon, then this R of x is going to be proportional to epsilon squared. The theta of x is going to be proportional to just the first power of epsilon. So you can separate them. You can see them as you need to separate geometric effects. Okay? And this R is going to be an orthogonal transformation. Orthogonal transformation, i.e. a rotation of the tangent space. Orthogonal means it preserves lengths of vectors. And lengths defined by the metric. But this is a shift. Right, so it takes the tangent space and it shifts, translates all the points in that tangent space by constant. And this is called torsion. Okay. So torsion has three indices, right? It's I, J, K, like that. Because it takes in two vectors that basically define this loop, infinitesimal parallelogram along which you're transporting. And then I is the vector that it spits out, the shift that you end up with. And So torsion-free condition is saying that nothing weird like this is happening, and when I go around the loop, the only thing I'm getting at is a rotation. The rotation is called curvature. Okay. Right. So in a crystal, I can have
But R is the orthogonal transformation.
yeah.
What's TR? Okay.
What?
TR is transformation.
TR?
What do you mean by what after the word
TR
orthogonal?
transformation. Yeah. Yeah. So in a crystal, I can have a conical singularity, which is like this. Imagine just like putting atoms in a rectangular grid like that. But there's a conical singularity somewhere. Then if I take, for example, a vector like that and do a parallel transport around the cone, then I will end up with a vector that's rotated by an angle that's proportional to the defect angle of the cone. And that's curvature. Curvature tensor is like a delta function sitting at that point.
The cone is not. Like what tensor is how transferred?
Just like the
But then the vector is the same.
there's a better picture.
But isn't the cone not inherently the sphere is inherently the cone? You can just make the cone like paper.
Yeah.
There's no. But,
No. But when you do parallel transport, it effectively integrates curvature over the area enclosed by that contour. It's not obvious, right? In this statement, the loop has to be infinitesimal. So infinitesimally, if I was transporting here, sure. But since there is a singularity, I cannot, I cannot contract the loop through the singularity and make this follow. So it is flat here, but it's not flat here. And this point, because it's inside of this loop, it affects the result. But anyway, I'll send you a picture of the crystal for the bit, so it's difficult to draw the atoms. Will be clear. Because here I have to specify the metric and blah blah blah, but when you just have a grid of atoms with the defect, then it's very clear what the shift and what the rotation are. So there can be certain defects that lead to torsion. But anyway, so how is the parallel transport defined? And what does that mean? Wait, so I take a covariant derivative of vector field along what?
Along some curve.
Along the curve, right? So along the along the velocity vector of that curve. And this has to be 0, and that means that x is parallel period. Parallel to what? Parallel to itself along the curve.
I mean, it says on the top.
Out of parallel.
Yes,
sure.
I don't know why.
Okay. It's parallel to itself, right?
But I mean, but you can choose any vector to that.
That's the geodesic, yeah.
The geodesic in here, the geodesic says you replace x with gamma dot, and they call it geodesic. I mean, in the textbook it calls it all the time.
So I have a curve, I have a vector field, like that. Okay. And if the covariant derivative of this vector field along the curve is 0, then we call this vector field how the parallel link is on that curve. Okay. What's important is that this vector field doesn't even have to be defined anywhere off the curve.
Yes.
Okay. As long as it's just an element of the tangent spaces along the curve. This means that if I parallel transport this vector along the curve to this point, I will get exactly the value of the vector field at this point. Right? So it is the parallel transport of itself. So again, it means that tau along gamma of x is x always for all distances. And this is the infinitesimal version of that. So the covariant derivative is just the infinitesimal version of the parallel transport. And then this is called a geodesic if the tangent vector of the curve itself is of a parallel. Why does that make sense? Well, for example, in the plane, I can take vector, I can parallel transport. In the plane, what does that mean? It means I take my vector here, and I measure the angle between that vector and the velocity vector of the curve, right? And I record this angle, 30 degrees, okay? And then I ask you, how do I parallel transport it to this point? The answer, it has to make the same angle. In the plane, it's easy. It has to make the same angle with the tangent vector. Because it's a straight line, it's going to give me the same answer. It's just the parallel, it's literally the parallel transport. Just measure 30 degrees, you get a parallel vector. What if this curve makes a break like this? It has to be 30 degrees with that. Right? So it actually rotated. Oh, sorry, that's not true. So I gotta be careful. So it makes a break. It means I transported it up to this plane, okay? And now I'm measuring the angle with the tangent vector here. And now it's more 90 degrees, okay? And then I transport again here, preserving the angle, 90 degrees. It's still parallel to this. And you can continue along any curve like this in the plane, you'll get the usual natural transport of but of course, if I take the tangent vector of the curve itself, if I want it to be a straight line, then it should be pretty obvious that I want the tangent vector to be transported to itself if I parallel transport it along the curve. That's what it means to be geodesic.
So the direction of V1 and V2 locally have to also be the same for the geodesics, like infinitesimally. Not locally, infinitesimally.
Wait, say it again?
The direction in which the velocity vector is pointing has to be the same.
Well,
infinitesimally.
Even infinitesimally, it's not clear what the word direction means, right? If you're comparing two different tangent spaces next to each other. That's what the connection is for. But yeah, they have to be the same with respect to the connection. Huh?
Then how are you measuring the angle?
Well, yeah, okay. So the angle, So the angle in Riemannian geometry is defined through the cosine. Right? The cosine, if I have two vectors sitting at the same point in the same fiber, then I can measure the angle by doing this. I take the dot product difference of g of x, y, and
But then
define by
can't
the
you
moment.
measure the angle between the two velocity vectors as well?
What?
Can't you measure the angle between the two velocity?
Yeah, so I can
vectors?
measure the angle between my vector that I'm transporting and the tangent vector to the curve, the velocity. And I can make sure that it's the same angle. But that's just one angle. So in higher than 2 dimensions, it's not enough to fix the vector completely. So you need to have more information. But
So what is the?
I'm just giving an illustration,
so
like
for a
in the plane it works. In higher dimensions.
Yeah. So for a geodesic, is what you drew geodesic, the geodesic equation?
So this one.
Not the equation, the transport, the picture. That's just parallel transport.
Yeah, that's just parallel transport along the broken line in the plane. I'm showing you that even if the line is broken, not straight, this is just the usual parallel transport.
So how do you, so what do you add for that to be geodesic, the tangent line of the...
Geodesic, the tangent line, yeah, the tangent vector for the curve itself has to be out of parallel.
Can't change.
Yeah, has to transport to itself.
Okay.
This is what the geodesic equation says. Okay. It's interesting that the geodesic equation is a second order differential equation in the gamma, and the potential in it is given by the Christoffel symbols. So you can think of the Christoffel symbols as the physical potential, which changes the shape of the geodesic trajectories. If you look at the equation, it's just like Newton's equation, but with some nonlinear term. Well, again, maybe it's not, I shouldn't call it a potential. It's multiplied by gamma dot. But yeah, it's some weird nonlinear force. Anyway, anyway, what else? I'm gonna skip the geodesic convex stuff. Okay, so Killing vectors are interesting. So Killing vectors are important, very important physically, because they are the underlying symmetries of the Riemannian manifold, right? Like all the simple models of general relativity that involve black holes or stuff like that, they always assume maximal symmetry in space. The cosmological models, the earliest cosmological models that were considered, you assume that the maximal number of symmetries in the space that you can have. And the symmetries are just the directions along which the metric stays the same, naturally. To formalize that statement, you need to take derivatives of the metric and equate them to zero, obviously. But the covariant derivative of the metric is already zero. So the only derivative we can take is the lead derivative. So if the lead derivative of the metric along the metric is zero, then that vector field is called a Killing vector field. It preserves the metric. And therefore, everything derived from the metric, the curvature, and so it turns out that you can write out the condition on the Killing vector field explicitly as a differential equation on x, and the differential equation is that Yeah. In components, it's this. But in not components, obviously. If you take this expression and contract it with a sufficient number of vectors, this is so this is some weird what happened there. Yeah, so we exchange y and z, which makes sense. That's what's happening in that one. All right. So if I take like a I don't know, like a hyperbola, embedded in the usual three-dimensional space, then what are the killing vector fields on the obvious ones? There are more than one, probably, but if each one you can guess immediately what's the symmetry of this shape. This is a circle. What's the vector field along which the metric would be that? There's only one obvious symmetry of this.
Cylindrical.
Huh?
Oh, just a circle? Or
Cylindrical.
What do you mean by that?
Me? Or him?
Laurent.
The or not cylindrical. I mean, like you can that like it's along the z-axis. It's symmetric across. If it were, I don't know how to say this correctly, but
What's the motion, right?
Cut through the middle by like the xy plane, and it's symmetric plus minus z. But I know that that's not the right way to say that.
Okay, that's discrete symmetry. That's not a flow of a vector field. Right? A flow of a vector field would be motion. Points moving. Rotation where? In what direction? Along the vertical axis.
yeah.
Do this and rotate. It's literally the vector field that goes along the, you said it right, along the circle. Right? That will be preserving the metric. Of course, the velocities of rotation here have to be coordinated in some ways, but it's obvious what it should be physically. You just rotate this rigidly. Right. On the sphere, the metric on the sphere, what are the vector fields? Yeah, also yeah. Any rotation. The sphere is actually maximally symmetric. There's a computation you can compute what's the maximum number of Killian vector fields, linearly independent Killian vector fields that are manifold of dimension n. The formula is, but you can compute them on the sphere and find out that it is maximally symmetric, as is the point.
There's two.
the plane I'm in are in.
So how would you, what does the killing vector field look like in this case? How would you express
In what case?
that it's a rotation around the vertical axis?
On the sphere?
On the hyperboloid.
No,
I mean, it doesn't
I just
matter.
described the vector field, right?
Hmm?
Didn't I describe the vector field?
I may have missed it because it got cut out.
Well, imagine rotating this thing with some constant angular velocity in physical space, right, along the vertical axis. And then the velocity of each point of this hyperboloid will give you the vector field, which is the killing vector field. So the velocity is proportional to the distance to the axis.
Yeah.
Okay. Oh, and one last thing is there's also a canonical way to integrate. There's a canonical volume form on the line, right? And then that's given by the epsilon tensor. Maybe it was not introduced in the book, but the volume form is also called the epsilon tensor, the Levi-Kikuta tensor. So in physics, you usually see these epsilon, ij, k used sometimes for cross products, etc. This is the one that's +1 for positive permutations and -1 for negative permutations. But this would not be a tensor, obviously, but because you cannot just take components of a tensor and fix them to be certain numbers everything. So you need to modify this somehow. And the modification is you take well, is there a natural way to derive this? Yeah, right. So locally, you take this volume form, it will act on a bunch of vectors, right? A bunch of vectors. And the result, they are all sitting at one point, P and and then the result must be the root of the determinant of the dot products of those guys. The matrix made up from dot products. In like the flat space, this would be literally the volume of the parallelogram that they form. But in general, this will be a tensor, which in local coordinates is root g, or you do not be confused because I'm using both index notation and abstract notation. Get g times dx1. So this is a differential form like that. And this that g is the determinant of the matrix Gij in components in these coordinates. The determinant, of course, is not in no way a covariant object because this is not even a matrix. So what the hell is the determinant?
Is the symbol on?
Yeah. What's the symbol where?
What's the symbol on the v's after mu? On the tangent.
Yeah, they all have to be in the same fiber, right? About the same thing.
I didn't hear that.
They all have to be in the
Can you
same
say that
fiber
again? I didn't hear
about
that.
the same point. Go on.
Yeah.
They have to be in the same fiber.
Okay.
Above the same point, right? Because we want to compute the volume of the parallelogram. Well, yeah. the idea. No, that's wrong. Should have gone for but so the point of this is that this differential form is not a differential form locally. Right? Locally it's dx1 dxn, so it is in that little patch it is a differential form, but it doesn't transform like a differential form locally. If you transform it to a different coordinate system, then it will get multiplied by what? By the determinant of the transition function. Right? That's a general rule for
change the basis.
Yeah, that's a general rule for differential top functions for any volume form, right? If I change coordinates, the result gets multiplied by the Jacobian. That was actually the definition of the Jacobian, right? This will get multiplied by that of some, the derivative of the transition function. Right? But then, what is the root of that g multiplied by? Well, g is a 0-2 tensor, which means it will get multiplied by the Jacobian matrix of f on both sides. Not f and f inverse, but 2x on both sides, right? Which means you have two inverses of the determinant of f here. And then you take the square root, and with 1 cancels with that. So the result is a covariant object. Okay? Right? No. So Gij under a change of variables goes to like f star inverse I k and then g k l and f again inverse l j. Okay. And when you take determinant of this will be the product of the determinants of this matrix, this matrix, this matrix. But this matrix is the inverse of this matrix. So these determinants, these two determinants cancel this one. So together, this thing doesn't transform. Transform it. It'll equal that g times dx and then in the new coordinates.
I'm missing a lot of
Is it clear why this transforms this one? It's a 0-2 tensor. Right?
Yeah.
So it's
you have the transition of.
So when you have a tensor of type RS, like every contravariant index gets multiplied by gets acted on by the Jacobian matrix because it's like a vector.
Yeah.
Vectors get covectors by the inverse of the
I see. Yes, no, not
yeah. So an object like this on its own, dxn, etc., dxn, exists also. Like it's not a nonsense. Okay. But it's not a tensor. It's what's called tensor density. You can do it like on your own. And you can also take the variant derivatives of tensor density, etc. So they transform not like tensors. They transform not like this, but they also get multiplied by actually root g. That'd be like the inverse of root g. But anyway, that's not super useful. So that's it. And I think the last thing I need to mention is the curvature, which is, well, I'm going to skip the Laplace operator. That should be pretty clear. Right? The gradient of a function is just literally d of the function and then raised. Right? So we have gradient of a function is just df, which is one form, and then you raise the index.
Very good. gradient as a vector. Because I learned that in one.
Yeah. So gradient f as a vector, I is just Gij, Dj. And then we know what the divergence of a vector field is. So you combine divergence with gradient, and you get Laplace. This is called Laplace-Beltrami operator. Okay. And then in differential forms, there's a different operator you can define, which is the Laplace-Hodge operator, or Laplace-de Rham operator, which is you take the differential form, you can act with D, you can act with Hodge star. I don't want to remind what the Hodge star is. Do you know what the Hodge star is? Okay, we can just look in the book. But anyway, so there's a natural adjoint of the exterior D operator. Basically, it's this. You can take a form. If this is, let's say, a K form. Okay, you can multiply it by another form, which is n minus k. This is not a power and not an index. This is the degree of the form. Okay? The result is an n form, which we can integrate over a manifold. Right? And if we require that this is the volume of n, right? This is just equal to the standard volume, then this is called star n, the Hodge star of n. So it's dual under the usual, L2 product that, in this case, differential terms on manifold. If you think of this as an L2 product. And so you can take D star, define it as star D star. So star takes you, let's see, so D goes from K to K plus 1, raises the degree of the form. Star goes from K to n minus k. Then D goes from n minus k, star, n minus k to n minus k plus 1. And then, once again, star gives you n minus this thing, which is k minus 1. Right? So star D star raises the degree by 1. So it's the natural kind of dual version of D. And so you can take and define another Laplace operator acting only on differential forms this time, not all vendors. Well, I guess that one after the functions. And this will be D star D plus D star. Just to make it symmetric. Nice. And what's weird is that you can prove that on functions, this acts on all forms, but specifically on functions, nabla is, this delta is minus nabla squared. Minus the Laplace. It's all strange. That's what it is. But this acts on all forms. And the Laplace-Beltrami operator, of course, can be generalized to all tensors this way. You take nabla I and nabla j. That's the second covariant derivative. And you take di. Kind of raise the index of one of the numbers. And this will be your Laplace-Beltrami operator acting on all tensors. So the wave equation, all physical equations, applying Gordon equation, whatever, they all use this operator. And the curvature is this thing.
I have to go in 10 minutes.
Huh?
I have to go in 10 minutes.
All right. Yeah, we're almost done. So the curvature, actually, I'm going to write it in this way. It is. Did I write it?
Yeah, I know that. I was just joking. So this is um, and then right. So I'm claiming. First of all, so what's the type of this tensor? If we prove that this is a tensor, what is how many indices does it have?
That goes off my screen on the top right.
Mm.
It goes. Is there anything after the minus sign on the top right?
Here? No.
Okay, and what is that Z bar after the parentheses?
No, just Z.
Okay.
So intuitively, the curvature tensor measures the non-commutativity of covariant differentiation. Okay. It might be a little strange that this term is here, but if we take x and y to be coordinate vector fields, like d, I, d, j, right, then they commute. So this term dies. So it's just a commutator of covariant derivatives in components. And so it takes in two vectors, which means two covariant indices, right? And it acts on the vector, and it spits out a vector. So one more covariant index and one more contravariant index. So this will be R. What's the notation used in the book? It's R, I, J, K, L. Okay. By the way, it is important, and some books neglect this, some authors neglect this. It is important to space out the indices and not write contravariant indices above covariant indices. Because later, like if I take a matrix, I take a matrix like this, a 1-1 tensor, and I want to lower the index, right? So I take G, I, K, A, K, J, right? I'm going to write that this is like A, I, J, or J, I. What is it? Which one? If I lower the index, right, this one collides with this, and it's not clear what the order is. If I want to state that this matrix is symmetric in some sense, I would need to write that this equals that, and then I have no problem. But if it's not symmetric, then no problem. So it's important to space out the indices always like this. And of course, I cannot just shift them around, so it's always, if you associated this index to this vector, then that's how it should be in all of the formulas. That is curvature. And then you can define a couple more important things. For example, you can define the reaching curvature, which is you take a contraction of these two indices, the first one and the fourth one. It's L, K, L, I, K, L. Okay. I.e., well, okay. Is it clear what a contraction is?
What is a contraction?
So you can, in general, you can contract only an upper index with a lower index.
Yes.
And that means you take any basis, and its dual basis, okay? Or dual basis like that. And you take your tensor, let's say it has only one upper and only one lower index. And you feed into it the alpha, EI and then alpha I. And then you sum over I. And you get your contraction. EI. So it's basically, it's just like the trace of a matrix, right? Literally the trace of a matrix. Plugging in a basis and a dual basis means just taking the diagonal with the same numbers, right? It means just taking the diagonal elements of the matrix representing this T. because it's a 1-1 tensor, it's actually a matrix, and it makes sense to talk about its components as a usual matrix. You take the trace, that's what that is. But in Riemannian geometry, because we have an isomorphism between tangent and cotangent, covariant, contravariant, we can always lower and raise the indices, so you can contract any pair of indices, but you just have to be careful to raise one of them or lower one of them if you need to. So this is the Ricci curvature, and then you take one more trace of the Ricci curvature, which is actually a symmetric tensor. It's a property of the curvature tensor. It's symmetric in those indices. So Ricci is symmetric. You take a trace, you get the scalar curvature. Okay. So for example, if you take the two-dimensional sphere and you compute the curvature, it's constant and equal to 2 over the radius squared. This is radius squared. If you remember, maybe from some Wikipedia articles or pictures, there's another curvature which is defined usually. It's much more used for surfaces, specifically two-dimensional surfaces. This is for any manifold, but for surfaces, you usually introduce the Gaussian curvature, which is the following: you take that surface and you cut it with a plane. Okay, hopefully, you cut it with a plane. And you find the plane and you compute the radius of curvature. Okay. Do you know what that is? So you take the section of the surface, which is a curve, and then you inscribe a circle into that curve, so it fits, as best. As good as it can. Take the curve and I fit a circle to it. And the radius of the circle is called the radius of curvature. And then the curvature of this curve at this point is called 1, it is defined as 1 over the radius. Okay? And then I take my surface, I cut it with all possible planes perpendicular to that surface at that point. And and of course, depending on the direction, direction of that plane, I will get different radii of curvature and different curvatures. So I find the smallest radius of curvature and the largest radius of curvature at that point. There's a theorem that proves that there's always exactly one, unless it's just constant in all directions. There's always one lowest radius and one highest radius curvature. And then you take 1 over r minimum, 1 over r maximum, and that's your Gaussian curvature at that point. So in the radius of the sphere, in the case of the sphere, this is going to be just 1 over r squared, obviously. So the formula is that k is the scalar curvature of the 2. That's the general relationship. And of course, you can see why how curvature is related to parallel transport. If I take a vector, let's say horizontal, on the globe, a vector that's horizontal pointing along the parallel, and I parallel transport it along that parallel, along that circle, make a full circle. Where is it going to come back to? So think about it. So basically this measures how far is this circle from being a geodesic. Right? It's not all geodesics on the sphere are the large circles, right? But that means that we need to kind of measure the angles, how much this vector is misaligned from the would-be geodesic, right? Through that point. So you can draw geodesic in that direction, something like that, and well, I don't remember what's the easiest derivation of this. I think Arnold actually proves this. It's the easiest to do on triangles. So you do a spherical triangle, right? This comes here, on the surface of the sphere. And the sum of the angles of that triangle, so these are arcs of big circles on the sphere, straight line, right? And you take the sum of the angles, it's going to be greater than 180 degrees by what's called the defect angle of the triangle. Okay. And it's obvious that if I take a vector here, parallel transported to here, it's going to point up just along the same curve because this is a straight line in this geometry. And then here the mismatch is just equal to this angle, and it's going to rotate to, let's make it not tangent, but like this, and then this, and then this. Okay. And the amount by which it rotates in the end is just going to be the sum of the angles. Right?
I gotta go.
Yeah.
Otherwise I'm gonna miss dinner.
Okay.
See you guys next week.
Yes, I should compute this. The difference, if the sum of the angles is 180, then it's just a flat piece, and it doesn't rotate at all. But if the defect angle is not 0, then it rotates by the defect angle. Okay. And on this theory, you can prove that the defect angle of the triangle is proportional to the area of that triangle. And in fact, any domain, you can take any curve on the sphere and compute the area of the part enclosed by that curve and divide it by radius squared. That's going to be the solid angle. And it's also going to be equal to the angle that you get after a parallel transport of along that curve. That makes sense. That's how it works. So, and this goes back to the formula that I wrote when I explained torsion, that the curvature is related to the, how big it's epsilon squared. It's proportional to the area, roughly proportional for small loops. It's proportional to the area of the loop. But that's a difficult theorem to prove, which I proved in my notes. But you can probably read it. I had to derive that proof myself. It just doesn't exist. And Arnold just states it in one of the appendices in the first appendix in mathematical methods of classical mechanics. He talks about curvature, and he just has this little statement that curvature is just infinitesimal. You take infinitesimal parallelogram, subtract it away, and you divide by epsilon squared. That's curvature. I kept looking for a proof that doesn't exist. Yeah. Second? Good. I mean, yeah, the proofs do exist, but most of them are based on the expansion. I mean, the second. Did you use Christoffels and the integration of Christoffels? Yeah, that's the proof that I don't like. Yeah. It's very non-covariant. It relies a lot